Yes, perfect. So then let's get started. I kind of need to. Okay, mute. I think everybody's muted. Okay. Okay, welcome everybody, lecture 7. This is getting the first lecture where we don't just talk about machine learning in general, but going into image processing, audio processing, video processing, multimedia data, as promised. Also, I'm going to update you about next week because I'm going to have an official tutorial at ACM Multimedia that is actually this class in a compressed version, which might be interesting for you to just see as an overview where this is all going. So I'm going to update you on that. Also, today is going to be a little different from what people may think. It's a little bit of physics, and I know people sometimes have sort of aversion against physics, or saying, "Oh my God, physics is what I hated in high school," or I didn't even take it ever. Don't worry about it. We sort of reinterpret the physics in a very computer science way and an information way, and so you'll see, but it is extremely, extremely helpful for us to do so, to understand why and how many convolutional layers we need and why they actually even make sense. Physics has usually been very good with explaining things, and so I chose that as the way to go. So bear with me a little bit. If you feel like, oh my God, this is so different, then I get it. Just ask questions and try to follow. And obviously, also the homework is going to build you a little bit towards that. Yeah. So with further ado, speaking of homework, please remember the project deadline. And then also, I send a demo project on Piazza, so people can take a look at it. In fact, maybe let's take a look at it together right now. So the demo project here is one from 2019, from the fall 2019 class. And so this was Rishi Puri. He ended up being my TA the semester after. And so the idea was there's currently no formal method for choosing the architectures for reinforcement learning. And so he basically used the techniques he learned in the class to then, first of all, he sort of literature reviewed what he learned in the class, and then he went and created an experimental setup with an algorithm that would automatically size a reinforcement learner on the fly. That by itself may be very interesting for you. This project was then put into Sergey Levin, and while I'm not allowed to say any grades, it was a very good grade. And also was a very good grade in my class. Again, I cannot tell, release grades. But the point is, it was exactly sort of the idea of let's do something and then understand how it could be experimentally designed and measured out. And he did that for data sets: blackjack, stock market, card pool, and Enchant. Not sure what it was, but he then measured the capacities needed and sort of sized the network automatically. And by doing so, he was basically getting also high accuracy and a very good generalization. So take a look at that. That was a very good project. You can do whatever you want, but it's also very nice that this project was actually creating something new, but it's not required. I'm completely okay if you go and just reproduce something and then analyze that. But this was creating new algorithms on top of the analysis. Okay, so that's on the Piazza. If you want to take a look at that, that it should be helpful. Yeah, any questions about that? Okay, I intentionally liked to give you this example because people were asking about reinforcement learning. So here's an answer. Okay, so that is number one. Number two is the homework. Homework 3 solutions were released yesterday. So this is basically what it is. The first question was, how much information in bits is represented by a clock with hour and minute hand, right? I kind of like this exercise because I think that's something nobody asked themselves that, right? Actually, if I have a clock, what's the maximum amount of information I can get out of a clock? Now we have to be careful because let's say it's light outside. Then also depending on your location, you may already know that it's not midnight, right? So that means you actually have less information. But so the maximum amount of information, say you were in a completely isolated room, but you had a clock, and you would otherwise have no indicator of the amount of information that of the time. Then you would have log 212 plus log 2 60 bits, because you have an hour hand, which could be in one of 12 states, and a minute hand, which could be in one of 60 states. And all you have to do is add those. And that ends up being, I actually didn't do the math here, but let's do the math. What you do is you do L12 plus L60, and that divided by 2, because you do log of 2. That ends up being 10 bits of information, right? 9.49, ceiling of that 10. Yeah, so 10 bits of information is as you watch, okay? And that's obviously assuming you know nothing about the time. So now we went to another idea. You have a compass. Assume you implement a binary classifier based on the direction of the compass, right? So you're saying the needle is north facing enough, okay? So you basically build something that stops if you're not going north enough, but will go forward if you are north enough, right? So it will turn and then go forward, right? And so you have a classifier that looks at the compass and says it's north facing enough. And now the question is, what is the maximum amount of information in bits that this compass classifier can represent? And that's very interesting, alternative visualization again of information. The answer is obviously 1 bit. It's 1 bit because in the maximum case, it would be north facing enough, yes or no, just like a coin toss. But that has to be only the case if you split the compass in the middle and assign the labels to each half. Okay, so it needs to be a 50-50 chance that the compass can be north enough or not. The moment you split it in different ways, and that's exercise B, you need to apply Shannon's formula, right? And so we have imbalance, sort of like 1% north and 99% is not north enough. Then you get to a class imbalance, and you have to apply Shannon's formula to find out the amount of information you can get per experiment looking at it. And now what you can do is you can say, okay, if that's not a binary classifier, if that's a general classifier, so multi-class classifier, what's the maximum amount of information you can train your compass to represent as a function of the number of thresholds? And yes, it's just log 2 of the number of thresholds plus 1, actually, so there's one threshold, log 2 of 1 would be, it needs to be number of thresholds plus 1. Sorry, that's basically wrong. So log 2 of the number of thresholds plus 1. Because log 2 of 2 would be 1, and exactly. So log 2 of the number of thresholds plus 1. So that's how you get to that, but it's maximum. So that means if you get to uneven distributions, it's not so easy. You have to use Shannon's entropy and then basically combine that. But right now the question is only maximum, and the maximum it would be even distributed, and it's just the number of thresholds per one. So next one, and again, questions about that? Okay.
Question.
Yes.
How would you compute, or how would you solve for the number of thresholds in a multi-class case?
Well, in this particular exercise, you basically saying I'm taking the compass and say north enough, south enough, east enough, west enough, right? And in order to do that, you create 2 thresholds, right? And now you have enough now you have 4 classes, right? And that gives you 2 bits.
Thank you.
Right? Now, in general, you don't. In general, you have to learn how to get to the number of thresholds or figure that out. And that's a different story. I mean, that's some measurement that needs to be done. But for this exercise, we're not going there. So neurons show that the maximum output of the threshold neuron is maximally 1 bit, right? Independent of the activation function. And of course, the hint is to exercise 2 first. Why? Because I explained it actually in the lecture. The information content of the output of a neuron is measured by the entropy. Entropy maximizes for the uniform distribution. That means for binary classifier, there's maximally an equal chance that either of the classification results appears. So it's either fire or not fire for the neuron, or you below or above the activation function, right? And so that makes it minus log 2 of 0.5 or 1/2 is 1 bit of information. Now you can, whatever distribution you have, you can skew that distribution and get less bits out. But you can never get more bits out, right? Because you can never get over 50 chance. So when we ask for the maximum, we don't really care about the activation function because the maximum is 50-50 chance, fire, not fire. The moment you put in a bias with some activation function, you can only lose information. I mean, you can model it, right? And then it's maybe not so surprising what comes out, but the point is, from an information perspective, you can only lose information. Now, Boolean functions. So we can draw the decision tree for the NAND function of 2 Boolean inputs, right? So that is quite simple. I mean, I can do it. I should have done it. Sorry, I just saw that it's the whiteboarding class. And yes, if we were in a normal class, I would just go to whiteboard and do it. And then the same you can do with the artificial neuron that implements NAND. And then you can draw the 3 neuron artificial that implements the equality for 2 Boolean inputs. We also did that in lecture already. So this is a little later. It's basically slide lecture 6. And then you can also draw a 2 neuron artificial network that implements equality for 2 Boolean inputs. And all you have to do is you invert the XOR network that I also showed in lecture already. And the funny thing is, you can change B, that means the NAND one, for non-Boolean inputs. Basically, just saying, okay, we have some analog, but we are basically quantizing it to be digital by just making sure that all weights and biases are either -1, 1, or 0. And so this is an interesting trick that you should probably just go through at some point and figure out. And the best way to figure it out is to just simulate it with the program. I've done it. I need to double check if I uploaded this program to the GitHub. If not, I can upload this program to the GitHub. That simulates like for all different inputs, and you see these thresholds just work. Then I gave you a little bit of a math exercise just for fun. Show by inductions that a half t to an n is the same as t and n. So that gives you sort of the defined in McLean's book. The information threshold at 2, n equals 1 is obviously the exception, and then you just do your thing, right? You take the anchor and just do it. Again, you can take a look at the solution and ask many questions. What you do is number 6, so is more interesting. Describe a process to benchmark practical implementations of neural networks based on the TNK function. And we have to remember here that the TNK function is sort of your optimum. Now the question is, how close can I get to the optimum? And that's how you benchmark. So the TNK gives you the baseline, and then what you do is you generate random points, and you test how many functions can be actually trained and compared against the theoretical limit. And the way you do that is you generate random points and you assign random labels, and you basically just continue. So either you assign the labels systematically, then you would go from 0 to n, but there's of course 2 to the power of n labels. But I mean, that would work. But if you can't do that, one thing to do is to just statistically sort of sample enough to hope to get to sort of a sampled number. And that's what we did. These are some of the results we had in the papers you saw, and also in the slides, where we basically went in for Keras, just generated random points and then sampled from the distribution to see how good it works. Yeah, and that was basically that. And it gives you a way to treat a neural network with all its parameters and hyperparameters and training activation functions just as a black box. And then you can measure out, based on these different ideas that are in there, how close do you get to the TNK function. And that gives you a quality measure of how efficient is the network actually in modeling something. Yeah, any questions? Yeah, in general, we had discussed all of this in lecture, but of course the homework is there to make things a little deeper, and it's optional anyway. But it's good, I think, for everybody to just take a look and make sure it's there's some basic understanding there, especially when you read the solution and then you feel like you don't understand. Please visit me in office hours or text on Piazza or something, because I think that's very important, that at least you understand why the solution looks like it does look. Okay, any more questions? Okay, then we can go to our lecture. Here we go. Boom. Again, questions in time. So as a reminder from last time, we wanted to deal with noise, right? So here's again lots of noise, and the joke is, of course, noise is original, right? So this is, for example, there's a couple of videos online that are pure noise, but of course, because they're original, they shouldn't be copied. They're actually copyrighted, right? So it just shows you a law issue, because copyright is based on originality. You can only copyright things that are original. Well, guess what? Every single noisy video is original. And so you can have content ID claims on noisy videos. And that's kind of interesting. But then the question is, why is it original? And it's original because it's not general. And it's not general because you cannot find a rule that could predict every point here. In order to reproduce the video, you have to know the original, right? Because it's random noise. Now, the interesting part here is, while for us, random noise doesn't mean anything, something had to generate it, and that was a rule, okay? So random noise doesn't actually exist. But it is interesting to think about. Now, let's assume we have random noise. How would we go about finding this rule? And of course, you could say, why would I find a rule in this random noise? Well, because put yourself in the shoes of a computer. The computer doesn't have the same context and knowledge that we all have. Like, we are way more attuned to our environment. So when you ask a computer to classify a cat and a dog problem, the computer really literally cannot predict the next pixel, right? So what it is there is that we want to find a pattern out of this noise, right? And we always have to remember that this is how it looks, right? When you train and put training images in, the training images are not how do you do that? Rulable. There's no rule yet, right? So you can, for now, just memorize them. But obviously, putting in convolutional layers, and this is what we're going to see, helps us cut down on very well-known noise before we actually look at the patterns that are in there. And also, similar things happen with perceptual compression, for example. So, what are we doing now? So the thermodynamics of information model for machine learning is that you have an unknown pattern. Cat, dog. When I say cat, dog, you all think of a different cat and a different dog. It's not clear what a cat and a dog really is. I mean, we all have some intuition because our brain has a pattern in there, but we can't really describe what makes a cat and a dog, because if we could, we wouldn't have to do machine learning, right? if we could know what a cat is a cat and a dog is a dog, we wouldn't have to do machine learning. All we would have to do is put that rule that we have in our head into the computer and say, if la la la, then cat, else dog, right? So we need to figure out what that rule is. And so the idea here is you have a pattern that is y, and it's unknown. So there's some unknown rule we don't know. And now the problem is that the only way to observe the unknown rule is through a channel of added noise, right? So all we get by taking a photo of a cat or a dog is X. That's our observation, right? And with that observation, we can go and try to do something, because what we really want, we want to take X and we want a machine learner to get rid of all that added noise in the channel and come out with a label. So come out with a decoded version of Y that just generates a label. Basically, we say, yeah, it's a cat or a dog. So we get to some Y hat that may not be the original pattern, but at least we'll put it good enough into a category that it's a cat or a dog. And so that's the information model. And so in physics, because in physics we basically only know about setting and resetting bits. That's based on the Maxwell demon. So the idea here is we can say is a physical interpretation of machine learning is it resets bits introduced by noise. Basically, because of the data processing inequality, we know that X has all the bits that make a cat or a dog a dog. And it has to be in there because we cannot create information. So all we have to do is set all the bits in X to 0 that do not belong to the unknown pattern. Okay. And we could also say it in a signal processing way, which is machine learning denoises an unknown pattern. And that's kind of interesting, right? So we denoise something that we actually don't a priori know whether it's noise or signal. And obviously the way to do it is to use many samples and find out over many samples. Otherwise there would be no chance. Now, here's something very interesting. So in 1892, I think, a guy from Berlin, a professor at Berlin University, Helmholtz, Nobel Prize in physics too, wanted to understand something. He wanted to understand when I have a machine. This was the age of new sort of industrialism, right? And when I have a machine, we can do all this physics, and we built the machine. It's awesome, but for some reason, there's always a loss, right? And he wanted to know how can we actually categorize this loss. And so for him, so A equals U. If you take the second term away, just A equals U is nothing but action equals reaction. Okay, so when you have Newton, right, then Newton told you something like E equals mgh, right? The energy for an apple to fall down is so and so much, and that would be your mgh would be your U, right? And then we know that you get to kinetic energy, which is 1/2 mv squared. But that's not the point. So the point is that you have potential energy, and that's then converted into kinetic energy. So the way to think about A is your kinetic energy, and U is your potential energy. And of course, your potential energy, just like a battery, will be converted into something you do with it. Okay? But the big problem for him was that there's always a loss. Why, when I charge a battery, doesn't all the energy just come out like Newton said, action equals reaction? No, it's not. Action equals reaction minus something. But what is this something? Where does it go, and what does it do? And he then came up with this formula, which actually is the Nobel Prize winning formula. He said, actually, it's very simple. We lose energy in two ways. In temperature, which is T, and after that, in uncertainty. And he was just saying, hey, I don't know what that S is, but at least I got temperature out, because whenever I move my machine, it gets warm. So that energy needs to come from something. So that's temperature. But that also, it doesn't account for everything. Temperature plus U potential doesn't make the energy that you measure coming out. There's something still left. And it's not small, it's a factor times the temperature. Okay. So he was like, okay, I will just call that S, and I'm happy because it's a constant factor. And now some interesting things happen later on, and that was that actually Gibbs decided we actually know exactly what S is. It is the probability. So Boltzmann actually said the S is proportional to the probability of encountering a microstate. So it actually has to do, and this is so counterintuitive, S is not something that has to do with nature. S is delimited by how you describe the system. Okay? And that made this such a leap, such a weird, completely very hard to understand thing. So we thought, here's nature, actually equals reaction minus some temperature and some other phenomenon that I don't know. But that other phenomenon, that S, is nothing else but some uncertainty left in bits based on the probability of encountering the microstate. And that took a long time for people to understand. So for us, we don't have to go through this in detail. I actually have a lecture on this, computation, data, and science. And it's a two-part lecture. I already gave it to you, the first part. The second part then goes from that decision tree into physics and why this makes sense. If you are more interested in why on earth does the rule now play a role again, and this temperature times sort of probabilities, really, take a look at that lecture, okay? But for us, we can say the following. So we know from Shannon that information is reduction of uncertainty. And it turns out, yeah, H, our information that we know as information entropy, is nothing else but the physical entropy divided by ln2. Why divided by ln2? Because the physical entropies usually use the natural logarithm, but we want to measure in bits. And that makes it very, very interesting, because now we measure in bits. And so if we go back to this formula, then we see that T times S is temperature times a bit measurement. We'll talk about that in a bit. But it's very, very useful to understand that it has to do with how you describe the system. So while U, and so how does it even work? While U is your potential, right? And you have to think about what U really is. U is a formula by the physicist. Only A is measurable. The only thing you can measure is like, how hard does the apple hit the ground on your head? But you cannot measure the prediction of how hard, right? That's your prediction. That's your model in your head. And so, yeah, so your model in your head, or the model by the physicist in you, that's in you, that actually has an influence on the loss. And that makes total sense, because if your model isn't good, obviously you will have a bigger loss when you actually measure, right? If your model isn't good, then you may derive from the measurement by a lot, right? So now that we have this, we can actually use this to understand deep learning. And this formula, by the way, is about the most general formula you've ever seen. It's a lot more general than E equals mc squared. This formula governs everything. If you ever contradict this formula, you're wrong. Okay, so this formula is the thermodynamics formula, and the thermodynamics is basically the constitution of science. You can create all your own special rules in science. You can derive whatever you want, please do. But if you contradict the constitution, you get into trouble. And the constitution is thermodynamics. So all systems follow this. Of course, there are a bunch of constraints on the system, but every system we look at follow this. It's just the truth, and it's very hard. There's other stuff. There could be pressure and volume and so on that you can take into account. But in general, when you have a rule and you then measure, there will always be a loss, and that loss is governed by temperature and entropy. And that's just really interesting. Now, let's make this real, okay? Let's go away from this super abstract notion of this formula into something that makes a lot more sense to us in the multimedia sense. So let's say we capture an image, right? As computer scientists, we always think images are just there on a hard disk, right? Here's a JPEG, let's work with it. But images have to be created somehow, right? And yes, you use your DLSR to do that and you click. But what actually really happens in the DLSR matters for how we understand the images, okay? And that's what I'm going to do right now. So first of all, let's think about light in a physical way. What's going on there? Well, we have a bunch of energy from the sun, okay? And what happens to that energy? Well, that energy in terms of photons bounces off different objects, right? So we see that here as sort of the stylized person. So bounces off an object means, bing, it means that you will actually lose some energy based on Helmholtz, because every process loses something. So what energy do we lose? Well, the energy loss is measurable as two things. The frequency, the waveform of the photon actually changes. And also the amplitude of the waveform also changes. And guess what? These two changes are well known to us. The changes in amplitude are what we call luminance. How bright is it? And the changes in wave are called chrominance. Basically what is the frequency on the spectrum and it's basically what we perceive as color. So now color and brightness are created by the loss of bouncing an object. Now, how can we see this? Well, here's how we do this. So what you see here on the left is a circuit that has just one photodiode, right? So not a whole DLSR, just one pixel. And this pixel is connected to an actual measurement thing. And of course, we would see that if the sun was going in directly into that pixel, there would be no resistance, and we would completely get the entire battery be short-circuited, and we would measure that short circuit in our actual, okay? And that's why also white is 255, 255, 255, because white is the max. Yeah, the sun directly hitting the thing. So now the opposite is 0, 0, 0, which is black. Is if I cover the sensor completely, the resistance goes up completely, and then our measurement is 0. And now what we're actually interested in is in the middle. What on earth is the middle? On earth, in the middle is actually not the sun directly going in, but the sun ray bouncing off an object, losing energy, and then we measure that with our measurement instrument, and then we get the full range between 0 and 255, right? And we measure that in our actual, okay? So now the interesting part is, as computer scientists, so as a physicist, you would actually just model this Rmax and our actual thing as sort of this circuit that you see here, or as an electrical engineer, and you would say, yeah, our actual, right? So what I measure here is the same as Rmax minus, obviously, that loss that the sun ray occurs when it hits an object. So minus n times h. So it would be Ts, right? Temperature times entropy. And for us, I will now change the notion from T, which is temperature, and S, which is entropy, to N, which is noise. So I will assume temperature becomes noise, because guess what? The sensor heating up doesn't help us in any way, shape, or form with the reading. So there's some noise in the reading. And H is the entropy that we just had from Shannon, right? So basically S minus S divided by ln2. And so that way we can say minus N times H. And that works. And now we ask ourselves, so as computer scientists, are we actually interested in R actual and R max? No, that's something the electrical engineer or the physicist does. We are really only interested, really only interested in one thing, which is H, which is the information content of the image. And the information content of the image ends up being what we really look for, but the problem is it's convoluted by N, by the noise. We don't want the noise, and that's of course the same as our pattern. So our pattern Y that we introduced earlier is basically has some information content H, and is obviously convoluted with the channel noise, and which is N. So the way to read this is the following. What we actually are looking here in this equation is only the number of bits that we're concerned about. So H is the number of bits of information content that actually describe the unknown pattern. N is the number of bits of noise content. And then we completely can just forget R actual and R max because we're not really interested in them. I mean, R max is 8 bits for 1 pixel, for example, right? So we know it's 8 bits minus the noise bits times the actual content bits gives you the actual bits of the image. Right? So we can, I often give an alternative explanation, which is this is the information explanation. Again, you have an object Y described by an unknown pattern. The ideal camera takes an ideal image X, but it's noisy. And so then you have a noisy image X head, and that noisy image needs some decoder to get to some prediction Y hat, which is not exactly the unknown pattern, but is correlated in such a way that you can say it's a cat or a dog, right? And that's the same way of looking at it. Now, here comes a very interesting observation. If you have a term like N times H, okay, how do you get to N? How do you get to H or N, right? So we don't know what H or N is. We only know it's N times H. That's derived from Helmholtz. So if noise and images are convoluted, then how do we actually find this out? Well, let's ask an oracle. And the oracle tells us N times H, I give you N. Well, that would be easy because then N times H, you just divide by N and then you have H. Now we don't have an oracle, too bad, you know. So what we do is we need to actually just do N times H and divide it by an approximate value and hope that we get H approx out. And if you do so, we could do that just empirically and just basically start with N equals 1 and then up the ante and see what happens, how the loss looks like. And it turns out if you do that, it looks exactly like that. And this curve should be familiar to you based on when we reduced parameters for neural networks last lecture. Now, the accuracy here, it starts at 100% accuracy, but if you do that, then you have no generalization because all you do is memorize those noisy images. You don't actually get the pattern out. But as you divide by N, bum, 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 as you kill more and more of the right bits of that information content, of that N times H, you get to the information content. And that means at some point, you will find a trade-off, which is called N approx. And then you know how many bits to kill for that noise. But also, if N gets too large, then obviously you kill everything. You just quantize every pixel to 1, basically, and that's it, or to less than 1. And then you have nothing left, right? Then you get to 0. So the trade-off is to basically find out how many pixels do I need to delete, and that will be our N. But the problem is, it's not just the problem is also, sorry, how many bits of each pixel do I have to delete? But the problem is it's not just the bits. You also need to know which bits to delete. Because right now it's just a quantitative explanation of bit loss, but it's not clear which bits to delete. So I have my my 8-bit pixel or 24-bit pixel. How many bits do I have to delete that are according to noise is one question. And the second question is, which bits are these actually? Which one is the noise? And that is actually the interesting part, because there's two ways of doing it. One is convolutional layers, and the other one is to use JPEG compression. And you'll see that if you use JPEG compression, which is what I'm going to show you here, you'll get to a much, much more measurable result. And once you get to a much more measurable result, you can be happy, because that gives you an idea of either not using convolutional layers or dimensioning your convolutional layers in that way. So again, we're looking here just for a quantitative result of basically a signal to noise ratio. So here's what we did. We took a lot of architectures. So convolution plus ReLU, convolution plus dropout, and so on. And we just basically used them for image classification. And we used this on many different data sets. We used this on ImageNet, we used this on MNIST, we used this on CIFAR, we used it on MIT traffic data. And we used architectures A, B, C, D, E, F. Okay, I only show you 3 here. And also all of these were different architectures. So basically a large scale experiment of different architectures. And what we found out is, as we put JPEG images in, and we will actually, what we do is we will just kill, basically have more and more and more and more compression in JPEG. It turns out not only does this curve, sort of based on the theory, accurately describe why things work the way they work, no, it also actually predicts, exactly that there will be this trade-off. Okay, and so what we did here is we basically took all the images from CIFAR-10, ImageNet, and MIT traffic data, and what we did is we decided, okay, we'll JPEG them, we'll keep them as original, and when you keep them original, you get here's CIFAR-10, you basically get this 85.5% accuracy. Okay. And then we also reduce parameters, and with less parameters in the network, you actually get a better classification than with more parameters. But that was just a side effect. The major point here is that we created this curve over all these different architectures that you saw there, just to empirically verify over the different data sets that it always looks like this, always. Okay. And so what did we do? Well, we took JPEG, didn't compress. Then we took JPEG and upped the ante on the compression. So in JPEG, you can basically just go and say compress more, compress more, compress more, compress more, until you actually get to the point where you don't see any of the image anymore. And so we JPEG compressed those images. And as we did so, the compression ratio is down here on the x-axis. We exactly followed that curve. And the trick here is that, by the way, the sort of at 0.8, right, that compression ratio, about 80% compression, that was where we think is about the noise ratio. So yes, there's a lot of noise in images. Also, again, it turns out that we then, as we used JPEG compression, we could totally get rid of parameters in those networks, because there was less information content to learn and less noise to reduce. So what it means is that, actually, sorry, the same information content to learn, but less noise to reduce. And that would obviously lead to training becoming easier. And guess what? That's exactly what happened. With the different architectures in mind, it was absolutely clear that we get a better compression ratio with a better classification accuracy with less parameters. So And that again was mean accuracy over a bunch of stuff. Now, we then redid the experiments with audio effects too. We were like, well, what if we used MP3 instead of JPEG? And MP3 is similarly sort of measurable, right? And we get again to a similar curve where nApprox is just before the sort of it breaks in. So all in general, all data that has been acquired through sensors obeys obviously that thermodynamics formula from Helmholtz. And that means that you need to find the noise sort of point and reduce the noise so you can find the patterns. The problem why we need convolutional layers is, and I'll show you a bit how we did this, is that it turns out you have, of the 24 bits in a pixel, 23 bits of noise, okay? So if you do ImageNet, even with a lot of classes, you need to get rid of 23 bits of noise on average per pixel. And so that's why we need all these deep convolutional layers to just get rid of noise, and deconvolute that n times h, so that the n goes to basically 0, and we reset all these noise bits, and we get to only the information content, of which we then actually can go ahead and build a classifier, right? And so it works for audio. And so the interesting part here is that you can now find even more. So we found out that over all data sets and over all experiments that we did with images, JPEG Q equals 20 was the point of nApprox for all data sets and for all experiments we took. So JPEG quality 20 was the point where we actually reduced noise, and we could get rid of basically most of the convolutional layers, and we just train decision layers. And that is basically based on how you calculate and going into the depths of the algorithm, 1 bit per pixel. So H is 1 bit, N is 23. And that makes total sense why neural networks and also lots of previous methods of machine learning have failed, because they were just not able to cope with the noise. And so that's why the computer vision field was for a long time engaged into feature selection, because that's basically all these methods of manually getting rid of noise, right? And just trying to concentrate on what matters. But obviously, there's nothing better than really a general method. And the two general methods that I know now are JPEG, because they are very general. You look on a JPEG image right now when you look at the video. And the other method is a convolutional network, because in the convolutional network, we trained it to basically know the bits to reduce such that the noise goes away. And Mason has a question. Hi.
Hi, Professor. So there's been some recent development in the field of network pruning. Do you think that's related to this? I think basically, I don't know if you're familiar with this part, but basically they will train the big neural network, and then they start pruning like weights or like neurons, like in the layers down to the down to the extent that, you know, sometimes they can prune like 99% of the weights, and they can the network can still perform reasonably well. Do you think that's related to this compression idea, or do you think that's something different?
Well, we did the same, right? Okay, I think there are two different ideas. The first thing here is that we tried different sizes of networks and just confirmed that if you reduce the noise up front, your network can be much smaller than you might think. That's this. But there's also obviously most of the content of the previous lectures that, and especially if you look at the TF meter app that I shared, then most networks that we use right now are just way too big, because people are like, I have compute, I don't care, right? So let's just train forever. The point is, networks don't have to be big. Kolmogorov already showed in 1956 that 3 layers are enough. Every function can be implemented in 3 layers, but you may need infinite number of hidden layer neurons. Having said that, it's hard to train that. So the practice becomes then that you add more layers, because that's easier to train, because as we know, previous layers, subsequent layers can only look at the information coming out of previous layers, which then in turn means that you have to, you can actually correct errors, and you can actually sort of, wiggle things out. But to your question in general, what I invite you to do is to just look at the TF meter app, right? tfmeter.exe, right? And when you go in here, you'll see pretty simply that if you train something simple, first of all, that doesn't work. That's already too much. So, okay, first of all, this example should just work with 1 neuron, right? It does, okay? But now let's add too many neurons, right? So we do that, and what you see is a high degree of redundancy, right? Especially if you add a lot more than you need, it just becomes so hard to train, right? Here we go, but it does train in the end, and you just see that all these neurons have the same threshold, right? So minus 0.97, it's all about 1, but also it looks the same, they're just mirrored, right? So bum, 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 bum. And that's why you can get rid of those redundancies completely. Training a network this way is just superfluous. Does that make sense?
Yeah, I think I understand that. Like with fewer neurons per layer, the like we're getting rid of a lot of redundant informations that we wouldn't need to train to start with. But I think what I was mentioning is that like what the network tuning people are doing is they train a huge network, and after they train it, they get rid of some of the neurons or the weights.
Yeah, and I don't understand why they're doing this, because if I was an engineer, and I'm an engineer, I would actually not build 1,000 bridges and then get rid of the ones I don't need. I would actually plan out the bridge and build the bridge that I need. And so that's the point of this class, is what you do is you start building networks that are the size that you need, and not prune down.
Okay, I see. Thanks a lot.
Yeah. So, good. But yeah, I mean, different sizes do matter. Okay. So, all of this is explained in those 2 papers that I would actually invite you to take a look at. This paper, the Helmholtz method, has actually been accepted in a slightly different version and has been presented in August. There's also people in my group that work with this on a follow-up for this. And then the understanding of results examples, you kind of have to resubmit at some point, but yeah, we're working on it. So that's, by the way, it for today. I didn't want to, because this is a lot of deep content, I didn't want to overdo it. I want to give ourselves a little bit time for discussion and for also project questions. So please move forward and well, let me know any questions and so on. So one more question that should come up right now, sorry, is that while I now figured out, when you now read those papers, you will see that you have to kill 23 bits to get to where you want. And now obviously the question is, how many bits are killed in a convolutional layer, right? Because that would give you the answer of how many bits you actually, of how many convolutional layers you actually need. And the answer to that obviously is, first of all, homework 4, and then also has to do with what does this convolutional layer actually do. And so often convolutional layers are quantizers, or they take one out of a matrix or something. And yeah, you just have to do the bit operation. You have to basically just say, okay, how many bits can be in that matrix maximally, and how many bits do I have after the layer? And then you know what your quantization ratio is. And we right now know we need a 24-to-1 quantization ratio. That's pretty steep. And that means most likely you'll need a bunch of deep layers, which again is what happens in reality. Any questions?
Oh, I have a question about, so I think, I don't know if, so it's in one of the previous slides, it was a while ago, but I kind of hold that question. So I think the question is about the analogies between compressions, like JPEG compressions, and like mask that's used in like early layers. That's, which, some of the like network architecture people have been doing now. Like, I don't know if you're, so basically there was this thing called the lottery hypothesis, and there's been work that's built on this. So basically they trained, they find out some good weights, that like things that will lead to good accuracy in the end. And they start on the same set of weights on a different task. And that usually means using like the same, activation. So basically they'll like they have masking layers, which basically if it's masked out, that means, those information are not being considered. So I don't know if this is analogous to the JPEG compression, I guess in the earlier part of this course.
Yeah, it is analogous to the JPEG compression, because ultimately all a neural network ever does is compression, right? So even your Boolean function neural network goes and says, I take the two variables in and make it one variable. I see two columns in and make it one column, right? That's already a compression. It's a relevance compression. So yeah, it is always related.
I see. Thanks.
Yeah. And also, by the way, I should say, oh, I forgot, this was a slide that I probably omitted. Remember that McKay, in his original sort of information theory scheme, saw the perceptron in chapter 40 sort of as a sort of just an encoder in the channel. Well, yeah, and the best encoder is a compressor, right? And then he measures the information capacity of the encoder, and ends up being 2, right? And so, yeah, everything is a compressor.
I think Alex has a question. He raises his hand.
Oh, Alex, please go ahead.
Hi. So I'm not like JPEG compression, but when you're talking about like comparing like compressing like images versus like the accuracy, and talking about like how you have like some bits of noise like per pixel, is that strictly like each pixel has like that same number of bits of noise, or is it like on average you have?
That's on average, yes. And that's the difficulty, right? The difficulty is that this thermodynamics and information only gives you the expectation, which is the average, right? And so to find out which pixels actually have a noise and which not is the trick. This is why convolutional training takes so long, and or why JPEG took a while to develop. And also, if you think about audio, they had to develop a whole psychoacoustic model to get rid of the bits that didn't matter. So that's not easy. That's glimpsed over by the simple formula. But the reality is that's the problem. But the nice thing with machine learning is that we get to the point where it's like, yeah, if you just size it right, all you have to do is training, and then maybe you just get it right. or not maybe, you pretty much just get it. And before we had to go in and manually have a JPEG committee, fight this out politically, and so on. Right?
So sorry, as a follow-up, like, are there methods for like content-aware like compression, such that you can like sort of like pre-process like the input images for like smaller like neural networks?
Oh yeah. So you mean content aware instead of not just trying to get rid of noise?
Yeah.
Yeah, that would be called features.
Oh, okay. Okay, thank you.
You can always have special features, right? So I mean, if you know you want to do face detection, right, then you actually know, okay, so maybe there's something about, you know, those verticals and horizontals, and then you bias your compression that way, which is content aware, right? Yeah, any other question? Okay, so please take the time now this week to start working on grouping for projects. I think the deadline was set on the 15th, as far as I remember. And you need to sort of definitely get going on the projects. So please take the time, group up, and send me your proposals by the deadline. Also, ask me any questions, and obviously have my office hours on Monday. So please show up there if you feel in any way insecure about your projects. I'm going to stop the recording now. Stop recording. Yes, stop recording. And why is this so difficult? Okay, I'm stopping the recording now.